In this lecture, we study the characteristics of JFET. In the previous lecture, we have studied the operation of JFET. Now here once again, we see that now condition number 1 is when we keep both input and output, VGS and VDS, both are 0 at the time, no current in this channel. So no current. Now output side we are giving, this is because N channel, we have to give the positive plate to the D and negative plate to the source, and here we need to apply the negative voltage. Now this is the VGG, and the voltage between the gate and the source is VGS, and the voltage between the drain and the source is VDS. Now here this is current flowing in this channel is ID current. Now in the first condition, if input voltage and output voltage both are 0, 0, no current is taking place, means what? No charge carriers are flowing in this channel. That we have already studied in the last lecture. Now the condition number 2. So VGS is equal to 0 and VDS is applied some positive. Now it is less than the pinch off voltage. Now some positive voltage is applied at the output side. Then what happens? Now here when we are applying the positive voltage, then the depletion width increases like this. Depletion width increases like this. Now for more voltage, now this is for, consider this is for the 1 volt and the second line is for the 2 volts. Like that, if we go on apply the VDS value, then the depletion width is increasing like this. Now more bulge at the drain, and here at the source there is no bulge. So this is because of the channel is offering some resistance. Already in the last lecture we have seen that if the channel is offering, now if I consider 3 resistor values or 4 resistor value for the equivalent diagram, if I am taking for the channel, now here if I applied the 2 volts, now here the voltage is 1 point, here the voltage is 0.5, 1 volt, 1.5, and so like this it is dropping the voltages like this. Means what? From the, we are going from the source to the drain. If we are going from the source to the drain, the positive voltage deposited is more. So that's why here at the near the gate, near the drain, more positive voltage is there. That's why here the more reverse bias. That's why here the depletion width is more compared to the source, near to the source. So that's why we get the depletion width like this. Now in this case what happens? Now VGS is equal to 0, VDS is applied because the charge carriers are flowing from the source to drain. So here if you take the characteristics for this one, now on the x-axis I am taking the VDS, on the y-axis I am taking the ID. Only one current is there, that is ID current in the order of milliamp. VDS is in the order of volts. When the VGS is equal to 0, when the input voltage is 0, or if the gate is kept open, that time only because of the VDD, now the depletion width is forming like this, and thereby here it is controlling the charge carriers. Now if we go on increase the VDS, linearly current increases up to 1 point, and after that the current maintains constant. Now this point is called as the pinch off voltage. Now this pinch off, what is pinch off voltage? If we go on increase the VDS or VDD, if we are varying the VDD, then at one point both the depletion width touch together, and it is now like it will touch like this, and this is called the pinch off region or pinch off state. Now here both are touching, thereby what? Charge carriers will not move from the source to drain. If no charge carriers are moving source from drain, means what? ID current is 0. If no current is flowing through this channel, means what? So no potential drop at the resistor, thereby there is no reverse bias in the channel. If there is no reverse bias in the channel, means what? It allows the current flow, charge carriers flows from the source to drain, thereby we get the maximum charge carriers after the V peak. After the pinch off voltage we get the maximum current, and this is called, this is the VGS is equal to 0 volts. Now at the time how much we are getting the maximum current, that current we call it as a VDSS, nothing but a maximum drain current. So now if we increase the input voltage, now this is for the input voltage is equal to 0. Now after the pinch off voltage, what is happened, I hope you understood. Pinch off, if both the regions are touching, when both the depletion regions are touching, no current is flowing. So because no current is flowing, no voltage drop is across this region, so no more reverse bias. That's why, so for it look like both regions are touching, but actually here, because of no reverse bias, so charge carriers flows from source to drain, that too maximum number of charge carriers are flowing, thereby we are getting the maximum current. And after the pinch of voltage, here it is going into the saturation. Here the number of charge carriers maximum limit is there. So once it is going to the saturation, it maintains the constant current. That's why we are getting waveform like this. Now if I increase the input voltage, increasing means what? Applying more negative voltage, reducing the less than 0. So if I am applying the less than 0, then what happens? Here this is VGS is equal to -1 volt. So with this what we understood. Now if I apply the negative voltage, now this depletion width increases like this, and after that by increasing the VDS on this again, the depletion width forms like this. Means what? We are going to get this V pinch off at early stage. The pinch off we are getting early stage as by increasing the input VGS. And also if you see the drain current reduces. Why? Because already in the last lecture we have studied that. Now here rho is equal to, R is equal to rho L by A, where the resistance is depending on the area. So now if the input voltage is increased, the depletion width is increasing, thereby the channel area is reduced. So it is offering the resistance. This resistance will oppose the current. That's why we get the less current as we increase the input reverse voltage. Now if you try to analyze this with the water tap, as you rotate the knob, thereby by rotating the knob you can control the water. So here also by giving the reverse voltage, so we can control the flow of current in this channel. So as you go on increase the input voltage, then the current will reduce. Now this is for -2 volts and so on. So at one point, so no current flows, so that is called the cutoff voltage. That point is called the cutoff voltage. Now this is about the drain characteristics. In the drain characteristics, what are we doing? So we are keeping the input voltage constant, and by varying the output voltage, we are observing the current and output junction voltage. For that, now these are the characteristics we are getting. So now in the and one more characteristics are transfer characteristics. Now for that we have to keep the drain. We have to keep the drain voltage VDS constant and vary the dVDS. Now in this case what? We have to keep the VDS constant. Now this we have to keep fixed. So VDS we have to keep fixed and vary the input supply voltage, thereby we get the characteristics like this. Now this is nothing but what? This we are getting from the same drain characteristics. Now if we observe the drain characteristics and transfer characteristics, from that only we are getting this. Now if we keep some voltage over here constant, and by varying this, if it is 0, then we get the maximum current. If it is 0, then we get the maximum current. As we go on increase the negative voltage, the drain current goes to 0, and where the drain current is 0, that point is called as a VGS cutoff point. VGS cutoff point. So this is about the transfer characteristics. Now both, if I show you at drain characteristics and transfer characteristics, it look like this. Now in this case you can see that if VGS is equal to 0, this is the maximum current we are getting. Now in the transfer characteristics also, VGS is equal to 0, then the same magnitude we get, current magnitude is same. And for -1, this is a -1. So where we are getting the constant current, that values we are getting. And here by increasing the VGS, now current is reduced. And at one point we are getting the VDS is equal to 0, that is called as a cutoff point, and in this magnitude is same as a pinch off voltage. Now here this is what? Where we are getting the constant current, that voltage we call it as a pinch off voltage, and this pinch off voltage and this VGS cutoff both are magnitudes are same, not the polarities but magnitudes are same. Now from these characteristics we need to calculate the GM, transconductance, that is the ratio of change in output, change in current to the drain current to the change in gate source voltage, that is nothing but a delta ID divided by delta VGS. Now similarly from this we need to calculate the RD. RD is the drain resistance, that is the ratio of change in drain source voltage to the drain current, that is delta VDS divided by delta ID. Now from this we need to calculate the amplification factor. Amplification factor is nothing but output voltage gain, nothing but a voltage gain, that is output voltage divided by the input voltage denoted by the mu. Now here in this case amplification factor is voltage gain. Now in the case of BJT, amplification factor is current gain we have taken. Now here the voltage gain is equal to output voltage delta VDS divided by delta VGS, input voltage delta VGS. Now for the same expression, if I multiply with the delta ID, then I can write this term as a RD and I can write this term as a GM. So now here the amplification factor mu is equal to GM into RD. Now we see the now we will try to calculate the drain current expression. Now drain current expression is, so now in the case of transistor, output current IC is function of the input current, that is nothing but a beta times IB. Now coming to the FET, ID is equal to IDSS. This is nothing but a maximum drain current, IDSS into 1 minus VGS by VP whole square. Now where VP and IDSS both are the constants, and these values we can get from the specification chart. Now at what voltage, if I am applying some voltage over gate, then for that voltage how much current I am going to get, that we can calculate by using this current drain current equation. Now for this I will show you a few problems. Now what happens if VGS is equal to 0? If input voltage is 0, then we get the maximum current. ID is equal to what? IDSS. If the input voltage is equal to cutoff voltage, then the ID value is 0. That already just now we have analyzed from the graph also. Now if the VGS value is between 0 to cutoff value, and if we apply some voltage, and for that what is the current value, that we can calculate by substituting those values in this expression. Now for that what we need? We need IDSS and VP value. So these we can get from the data specification sheet. So here those values are given, and VGS is equal to -1. If at -1, how much the ID value, that we have calculated by using this expression. So this is about the ID current, and these are the circuit diagrams. Now when VGS is equal to 0, then ID is equal to maximum, VDS is equal to greater than V peak is nothing but what? Cutoff, then at the time ID is equal to 0. Now if the VGS is in between V peak and our VGS cutoff and 0, then at the time, now this is a circuit, at the time we get some ID. That ID can be calculated by using the drain current expression. Now this is about the two characteristics of the FET. Thank you.